Hello everyone. Today let's go over a hard question that I just solved on my own. Again, I'm really happy about this because I just came up with it without any assistance after struggling with it for a long time. So I'm going to go ahead and show you how I did it. This is a binary search prefix sum hard question called count of range sum. And basically the ask again is not too hard. So basically what they want you to do is just find how many subarray sums are in the range lower to upper, right? It's not a really hard ask, but the challenging part is optimizing it. So let's go ahead and do that. Let me show you the brute force approach, which is how I did it, which is just going to be current and then get all the subarrays. Again, current plus equals 2 nums of j, starting at I, right? And then just ask if lower is less than or equal to current is less than or equal to upper, then that's another subarray that's valid. And then at the end, you just want to return the frequency of subarrays. So let's submit this. So that's what I first came up with. This is n squared, obviously, so it's not going to work since this is a hard question. But at least we understand what the question's asking, which is not hard, which is good. And we get time limit exceeded. So let me show you how I managed to optimize it. So basically, if you make some observations here, if we want to find all the subarray sums, the first thing I thought of was, hey, there's a hash map problem called subarray sums equals to k, but that's just for k. How do we find it within a range? So let's go ahead and first do the prefix sums of all nums. So because, for example, if you want to get the subarray sum of this, it's the prefix of the current minus previous minus 1. If we have an array of, let's say, and this is important, 1, 2, 3, 4, 5, we want the sum of this subarray. It's going to be prefix of this minus prefix of this to get this. So basically up to this point minus everything before is whatever the sum of this is. So let's go ahead and do that. Let's print p. Cool. So again, to get this subarray sum, it's 2 minus 2 is going to be 4, right? 5 minus 1 is 4, 2 minus 2. So standard prefix sum there. And now let's just go ahead and iterate over nums or over p. It doesn't really matter. They're the same size. So now what are we going to do to find the subarray sums that are in this range? Well, basically, since you know that we want to calculate the subarray sums, you know these are the subarray sums, right? So if let's calculate the subarray sum of this, it's going to be this minus this. So if I is bigger than or equal to 1, then we have negative, right? So negative, we subtract something, which is just going to be p of I minus 1. Otherwise, if I is less than or equal to 0, then now is equal to 0 because we don't subtract anything, right? So the idea here is just to go over p to the n, just like we did with the double loop. And then we can say if lower is less than or equal to a minus now, less than or equal to upper, answer plus equal to 1, and then return answer. And I'll explain why this is because, again, you're just trying to find answer is the result. So answer, again, we're trying to find the current subarray sum from the current point onwards. And the way you do that is by, let's say, here and here. If you want to find this subarray sum, it's just this subarray sum, it's just this minus this. So that's why minus the previous is this guy right here. If we don't have a previous, we're here. We want to find the subarray sum of this. It's just minus 0 is whether you minus 0 from a negative or positive number, it's the same thing. So we just set that there if we're on the first element. Otherwise, we have previous elements, and we can say that there's a previous element before the window starts, right? So subarrays like that. So is there a previous or not? That's the point of this. And then accordingly, we're just going to subtract, same thing. So we're just pre-computing the prefix sum. So now the challenge is how do we find this without iterating over this whole thing? So I got stuck here for quite a while. And then I just tried a couple things and then I was able to solve it. So let me show you what I came up with. So the idea here is since this is not even sorted, we need to sort that, right? And how do we do that efficiently? Well, let's just say SL is sorted list of PI to the end. So let's print SL and P of I to the end just to make sure we have what we want. Cool, so this is just a sorted version of this. And now we can do the binary search because again, if we want to count how many minus now, which might be 0, is going to be in this range lower to upper. We already know that we don't care about the ordering, because as soon as we find one, like for example, if it's valid up to this point, because -2, let's say now is 0, -2, it's up to valid up to this point, right? 3 is not. So in that case, we would just count 2 more subarrays, right? Like here, we just say 1, 2, 1, 2, same thing. So the order doesn't really matter in that regard. And that's what makes it easier, because we can just use the binary search, and we're still looking at the prefix sums of everything up to the end, but we're sorting those as well. So now what I'm going to do is say, and again, we have to subtract the now, which is a pain. So let's find the left boundary and the right boundary of when whatever current number minus the now is within this range. So since we're subtracting now, let's just go ahead and add it back, because if we say each number minus now, it's the same as saying, you know, the whatever the lower bound plus now, right? This minus now is the same as lower plus now, because we're still going to compare it to lower. So let's call this left bound, and right bound is bisect left inside of SL, right? Because binary search needs to be sorted. And then we offset the subtraction. So let's say lower plus now. So that's left bound, and bisect left finds exactly where that element is, because it can't be bigger than, has to be less than or equal to upper. It can't be bigger than upper inside of SL upper plus now, right? And since that's still equal, we want to do bisect right, which would be the very first element where upper plus now is bigger than the current element. So now what we can just do is make it really easy, because we can just say answer plus equals to right bound minus left bound. And as you can see, if we submit it, you get output limit exceeded. We have to get rid of this. And again, took me quite a while to come up with this, and I'll go ahead and show you what this is, because it's probably not really clear. And let's also print SL, and then let's do now, because we have to subtract everything from now, right? So now the let's get rid of this. Cool, so that's easy. But like in this, if we want to subtract 2, what are we going to do? So our bound is still lower and upper, so let's print lower and upper. So as this example, if we do 2 minus 2, which is now, is still 0. 0 still falls in this range, so that's good. And then here, 3 minus 2 is 1. 1 still falls in between this range, -2 to 2. So then the left and the right bound is 0 and 1. Let's call this bound. And here, for example, so 0 minus 2 is still within this bound. Sorry, this is supposed to be the bound. That's the range they gave us. Cool, so now the bound is 0 to 2. Why? Because this is in the range, and then this is within the range as well. So we have 2 elements, so that's why it's 2 minus 0, because again, if we did bisect left, it would go 1, 1 minus 0 plus 1. Instead, you do the index plus 1 to offset it to get 2 elements, like I said previously. And then this right here, again, 2 minus 2 is 0. That's in this range. The right bound is 1. 3 minus 2 is 1. That still falls within this range. So 0 and 1 are valid. And here, obviously, 2 minus 3 is, or this is the bound, this is the bound, this is the bound. Sorry, I was looking at the wrong one. This is, I guess here the left bound is 2 minus 2 is 0, and then 3 minus 2 is 1. Those both fall under the bound, so I'm not sure why it doesn't say that there, but here, you know, a good example of just one element being So -1 falls between this, so that's 1 minus 0, and that's +1. So let's go ahead and look at this one as well, or this example is probably a little bit strange because, so 2 minus -2 is actually +2. So that's why it does not fall under the bound. Here, 3 minus -2 is 5. They both don't fall under the bound. That's why the left and the right are both 0. So we don't have anything that's valid, right? So again, this bisect comes in handy for this. And then to get rid of the time limit exceeded, instead of doing this, let's just pre-process P. And then let's just do a discard, right? SL.discard P of I once from the beginning to say we want everything from the current point to the right. So this is for the next turn. And this is, let's see if this passes. Okay, time limit exceeded. Okay, instead of discard, that might be a little slow. Let's call this left index is bisect left inside of SL P of I. We just want to pop that element. So delete SL L of I, which is really just the first index appearance inside of the sorted list where this appears. So let's run this. Okay, that's still slow. Let's submit this. (3,800 milliseconds). Okay, so instead of delete, maybe that's an N operation. So SL.pop LI. Let's run this. And let's not make this a sorted list, because let's just make this P and then sorted P, because sorted list has N log N computation. So let's do delete SLLI now. So this is just a regular array, right? Because it's already in sorted order based on, we're just deleting the first occurrence of that smallest or that element without messing up the rest. Let's run this. And as you see, that's a lot faster than the sorted list. So let's do this again. And there you go, it passes all test cases. So again, just a little workaround there to get over the time limit exceeded. And again, really fast and decent memory. So I'm really happy that I solved this on my own. Again, it took a lot of work, but I think it was worth it. So yep, that's it for this video. I know this one's a little confusing, but hopefully this wasn't too bad. And thank you for watching, and stay tuned for more.